Good day, everyone. I am Nia Silvar from Team Gadolinium together with my groupmates, Ron Vincent Fabian, Jana Magpusti, Pichias Martinez, and Natalie Crepon, and we will be discussing about the concepts of stoichiometry and its applications in quantitative analysis. Specifically, we will tackle about the following subtopics. First is an overview about mass relationships and the proper writing and balancing of chemical equations. We will also talk about the different chemical reactions and the determination of amounts of reactants and products based on the types of chemical reactions. And finally, are the determination of percent composition and molecular formula.
Mass relationships. A mass relation refers to the ratio of the mass of reactants and products to each other. In a balanced chemical equation, you can use the mole ratio to solve the mass in grams. You can use an equation to learn how to find the mass of a compound, provided you know the quantity of any participant in the reaction. It says here that if you know the quantity of one participant in a reaction, then you can solve for other information of other participant providing that you have a balanced chemical equation. Steps in converting between masses of reactant and product. First is to convert the mass of one substance to corresponding number of moles using its molar mass. So in this step, we will be using the molar mass of substance A to convert to moles of substance A. Second is from the balanced chemical equation, obtain the number of moles of another substance from the number of moles of substance A using the appropriate mole ratio. The mole ratio here is the mole ratio of their coefficient in a balanced chemical reaction. Using this mole ratio, we can convert the moles of substance A to the moles of substance B. Third is to convert the number of moles of substance B to mass using the molar mass. It is important to remember that some species are in excess of by virtue of reaction conditions. For example, if a substance reacts with the oxygen in the air, then oxygen is in obvious excess, but unstated. Flowchart for stoichiometric relation involving pure substances. Step 1. Mass to mole. If you have a mass of A, we can convert it to mole of A by multiplying it to 1 over the molar mass of A. The step 2, mole to mole. From moles of A, we can convert it to moles of B using their mole ratio in a balanced chemical equation. In the step 3, mole to mass, now that we have the moles of B, we can convert it to mass by multiplying it with the molar mass of B. Simple example, how many grams of oxygen are consumed when 4 grams of ethane combust? First, we form a balanced chemical equation. Then, we use the mass of ethane, which is 4 grams, and multiply it by 1 over the molar mass of ethane, which is 58.1, to get the moles of ethane, which is 0.0688 moles. Then, multiply the moles of ethane to the mole ratio of oxygen and ethane, which is 13 moles of oxygen over 2 moles of ethane, to get the moles of oxygen, which is 0.447. And from moles of oxygen, we multiply it by the molar mass of oxygen, which is 32 grams per mole, to get the mass of oxygen, which is 14.32 grams of oxygen. Example in using mass relationship in solving standardization of acid and base solution. A 0.128 gram sample of KHP, potassium hydrogen phthalate, required 28.54 ml of NaOH solution to reach the phenolphthalein endpoint. Calculate the molarity of the NaOH. From here, we can list the given data, which is 0.128 grams of potassium hydrogen phthalate and 28.54 ml of NaOH. First and foremost is to get the balanced chemical equation of our problem. Then, since we have the mass of KHP, we can use the mass to mole relation to get the mole of KHP. Now that we know the moles of KHP, we can convert the moles of KHP to the moles of NaOH using the mole-to-mole relation and their mole ratio. Lastly, now that we have the moles of NaOH and the volume of NaOH is given, we can use the simple formula of moles over liters to get the molarity of NaOH. Here's another example. The combustion of hydrogen with oxygen to produce gaseous water is extremely vigorous, producing one of the hottest flames known. Because so much energy is released for a given mass of hydrogen or oxygen, this reaction was used to fuel NASA space shuttles, which have recently been retired from service. NASA engineer calculated the exact amount of each reactant needed for the flight to make sure that the shuttles did not carry excess fuel into the orbit. Calculate how many tons of hydrogen a space shuttle needed to carry for each 1 ton of oxygen. First, as always, we need to make a balanced chemical equation. Since the given mass of oxygen is in the unit of tons, we should convert it to the units of mass in grams by using appropriate conversion factors. Now that you have oxygen in the unit of grams, we can use the mass to mole relation and use its molar mass to convert it to the moles of oxygen. Now that you have the moles of oxygen, using mole to mole relation and the mole ratio of hydrogen and oxygen, we can get the moles of hydrogen. After we get the moles of hydrogen, by using the mole to mass relation, we can get the mass of hydrogen by using its molar mass. And lastly, we convert the mass of hydrogen in grams to tons using appropriate conversion factors. Now, we can see that a space shuttle had to be designed to carry 0.126 tons of hydrogen for each 1 ton of oxygen.
Chemical reactions and chemical equations. A chemical reaction involves a process where one or more substances undergo a transformation such as the breaking of bonds within reactant molecules, followed by the formation of new bonds within product molecules resulting in the creation of a new substance. It is omnipresent, influencing various aspects of our surroundings. Chemical reaction plays a role in processes such as the metabolism of food within our bodies and even contribute to the generation of sunlight. During a chemical reaction, a significant change occurs alongside observable physical alterations like precipitation, heat generation, or a color change. Additionally, the rate at which a reaction proceeds is influenced by factors such as pressure, temperature, and the concentration of reactants. These factors collectively determine the speed at which a reaction occurs. Given the multitude of chemical reactions occurring in our surroundings, a standardized nomenclature has been devised to simplify the expression of these reactions in the form of a chemical equation. This system allows for a clear and uniform representation of chemical processes, aiding in communication and understanding within the field of chemistry. A chemical equation serves as a mathematical statement that uses chemical symbols to illustrate the changes that occur during a chemical reaction, while also indicating the specific conditions under which the reaction occurs. In a chemical equation, the reactants are typically listed on the left-hand side while the products formed are shown on the right-hand side. These are connected by one-headed or two-headed arrows. For instance, look at the given reaction. Here, capital A and B represent the reactants with small letter a and b as their numerical coefficient respectively, that undergo a chemical reaction to produce the products capital letters C and D with small letters c and d as their numerical coefficient respectively. In chemical equations, reactants and products are represented by their chemical formulas. To adhere to the law of conservation of mass, which states that mass is neither created nor destroyed in a chemical reaction, a chemical equation must be balanced. This involves ensuring that the number of atoms of each element on both sides of the equation is equal, a process known as balancing the equation. And now consider what happens when methane burns in air to form carbon dioxide and water. This reaction can be represented by the chemical equation shown, where the plus sign means reacts with and the arrow means to yield. Thus, the symbolic expression can be read: one methane molecule reacts with two oxygen molecules to yield one carbon dioxide molecule and two water molecules. The reaction is assumed to proceed from left to right as the arrow indicates. In the equation, methane and oxygen serve as the starting material in the chemical reaction called reactants, while carbon dioxide and water serve as the products, which are the substances formed as a result of a chemical reaction. And to provide additional information, chemists often denote the physical states of the reactants and products in a chemical equation using symbols such as G for gas, L for liquid, and S for solid. For instance, look at the given reaction wherein both the reactants and product are in gaseous state. Knowing the states of the reactants and products is particularly valuable in laboratory settings. This information not only enhances the precision and accuracy of experimental procedures, but also provides valuable insights into the physical properties and behaviors of the substances involved. And now we have the different types of chemical reactions, which include combustion reaction, decomposition reaction, neutralization reaction, redox reaction, precipitation or double displacement reaction, and synthesis reaction. A combustion reaction involves the reaction of a combustible material with an oxidizer to produce an oxidized product. The oxidizer is typically a chemical if fuel requires to burn, with oxygen being the most common example. For instance, let's consider the combustion of hydrogen gas as an example. Here, two hydrogen molecules react with an oxygen molecule, yielding two molecules of water and releasing some heat in the process. While a decomposition reaction involves a single compound breaking down into multiple products, this process often requires external energy inputs such as heat, light, or electricity to break the bonds within the compound. For example, let's consider the decomposition of calcium carbonate, which yields calcium oxide. Here, the compound calcium carbonate decomposes into calcium oxide and carbon dioxide when heated. And for a neutralization reaction, it involves the combination of an acid and a base to produce salt and water as the products. The water molecule is formed by the combination of hydroxide ions from the base and hydrogen ions from the acid. The overall pH of the resulting products from the neutralization of a strong acid and a strong base will be 7, indicating a neutral solution. For example, let's consider the neutralization reaction given. Here, hydrochloric acid and sodium hydroxide react to undergo neutralization reaction, yielding sodium chloride and water as products. Meanwhile, a redox reaction or reduction oxidation reaction involves the transfer of electrons between chemical species. Let's examine an example of a redox reaction in an electrochemical cell, such as the reaction between zinc and hydrogen. Here, a zinc atom reacts with two positively charged hydrogen ions, and during this reaction, electrons are transferred from the zinc atom to the hydrogen ions, and as a result, hydrogen atoms combine to form a stable hydrogen molecule, while zinc ions are produced as the reaction proceeds. And for the precipitation reaction, it is a reaction where two compounds react and the cations and ions switch places to form two new products. And consider the reaction between silver nitrate and sodium chloride. Here, the reactants undergo a double displacement reaction wherein silver replaces sodium in sodium chloride and sodium joins with nitrate resulting in the formation of solid silver chloride precipitate and aqueous sodium nitrate. And lastly is the synthesis reaction, which is a fundamental type of chemical reaction where multiple simple compounds combine under specific conditions to produce a more complex product. The resulting product is always a compound. Let's consider the synthesis reaction of sodium chloride. Here, two atoms of sodium reacted with chlorine gas to yield solid sodium chloride. And once all the reactants and products have been identified and their correct formulas have been written, they are arranged in conventional sequence with reactants on the left separated by an arrow from products on the right. However, at this stage, the equation is often unbalanced, meaning the number of each type of atom on one side of the arrow differs from the number on the other side. And to balance a chemical equation, the following steps are typically followed. Number 1, identify all reactants and products and write their correct formulas on the left side and right side of the equation respectively. Then, begin balancing the equation by trying different coefficients to make the number of atoms of each element the same on both sides of the equation. We can change the coefficients but not the subscripts because changing the subscripts would change the identity of the substance. And first, look for elements that appear only once on each side of the equation with the same number of atoms on each side. Then the formulas containing these elements must have the same coefficient. Therefore, there is no need to adjust the coefficients of these elements at this point. Next, look for the elements that appear only once on each side of the equation but in unequal numbers of atoms. Balance these elements. And then finally, balance elements that appear in two or more formulas on the same side of the equation. And lastly, check your balance equation to be sure that you have the same total number of each type of atom on both sides of the equation arrow. To demonstrate this approach, let's use the combustion of N-heptane as an example. First, identify the most complex substance. The most complex substance is the one with the largest number of different atoms, which is the heptane. We will assume initially that the final balanced chemical equation contains one molecule or formula unit of this substance. Then, adjust the coefficients. Try to adjust the coefficients of the molecules on the other side of the equation to obtain the same numbers of atoms on both sides. Because one molecule of N-heptane contains 7 carbon atoms, we need 7 carbon molecules, each of which contains one carbon atom on the right side, giving us one heptane molecule plus one oxygen molecule yielding 7 carbon dioxide molecules plus one water molecule. And then third, balance polyatomic ions as a unit. However, there are no polyatomic ions to be considered in this reaction. So now we will balance the remaining atoms. And because one molecule of N-heptane contains 16 hydrogen atoms, we need 8 water molecules, each of which contains 2 hydrogen atoms on the right side, giving us the equation of 1 N-heptane molecule plus one oxygen molecule yielding 7 carbon dioxide molecules plus 8 water molecules. The carbon and hydrogen atoms are now balanced, but we have 22 oxygen atoms on the right side and only 2 oxygen atoms on the left. We can balance the oxygen atoms by adjusting the coefficient in front of the least complex substance, which is the oxygen molecule on the reactant side, which gives us the final balance equation of 1 heptane molecule plus 11 oxygen molecules yielding 7 carbon dioxide molecules plus 8 water molecules. And to check if the equation is balanced, we have to count each type of atom on both sides of the equation so we can check if the balance equation is correct. And now try to balance the given reaction. You can pause the video to answer it. So the balance equation of the given reaction is shown in letter A. Therefore, letter A is the correct answer.
Now that you have an idea about chemical reactions and how to properly balance chemical equations, let us tackle about the determination of amounts of products and reactants using stoichiometric calculations. In order to use stoichiometry to run calculations about chemical reactions, it is important to first understand the relationships that exist between products and reactants and why they exist, which require understanding on how to balance reactions. Just like in the chemical equation in the slide, which shows the reaction between 2 moles of sodium and 2 moles of hydrochloric acid to yield 2 moles of sodium chloride and 1 mole of hydrogen, the coefficient factor which converts the ratio of hydrogen to sodium helps convert quantitative data about one reactant or product to another. It is crucial for solving stoichiometric problems. As an application in quantitative analysis, acid-base equations are characterized by simple stoichiometry. So first, for when the reaction involves neutralization of a single hydrogen or for monoprotic acids, it uses the general formula of HX plus MOH yields H2O plus MX. While for diprotic acids or when two hydrogens are neutralized, it uses the general formula of H2Y plus 2MOH yields 2H2O plus M2Y. Then when for it is for triprotic acids or three hydrogens are neutralized, it uses the general formula of H3Z plus 3MOH yields to 3H2O plus M3Z. The millimole relationships may be converted into volume relationships through the definition of molarity, which is shown below in the equation. As an example, we have the permanganate oxidation of ferrous iron proceeds in an acidic solution according to the reaction. So the question is how many ml of 0.0240 molar manganate ion is required to oxidize 20 ml of 0.112 molar iron 2 plus. So for our solution, the stoichiometry requires that millimoles of iron 2 plus is equal to 5 times the millimoles of permanganate ion. Substituting values, we will get 0.112 and 20 ml for the volume. It's equal to 5 times 0.0240, which is the molarity of the permanganate ion, times X, which is the volume that is needed, and we will get the value of 18.7 ml as our answer. For another example, we have another problem. A blood serum is analyzed and found to contain 102.5 micrograms of calcium 2 plus per ml serum. The density of the serum is 1053 kilograms per cubic meters. The atomic weight of calcium is 40.08. What is the calcium 2 plus concentration in terms of A. Molarity, B. Milliequivalent calcium 2 plus per liter of serum, and C is ppm of calcium 2 plus by weight. And these are the solution for each question. For question A, we will get 2.557 times 10 raised to negative 3 molar. And for the milliequivalent, it is equal to 5.115 milliequivalent calcium 2 plus per liter of serum. And lastly, for the parts per million concentration, we will get 97.34 ppm by weight. For our third problem, we have the iron, tin, and titanium in a sample were jointly precipitated as hydroxides, which were washed and ignited to produce iron oxide, tin oxide, and titanium oxide. This mixture of oxides, which amounted to 0.3768 grams, was dissolved after fusion with potassium pyrosulfate. Analysis showed that 0.0322 grams of titanium was present. The iron was determined separately as an oxide. 0.1837 grams iron oxide was found. What was the weight of tin in the sample? And there are given molecular and atomic weights of the compounds. So to solve this problem with using basic dimensional analysis, we will get 0.3768 grams of tin.
Let us discuss percentage composition. Percentage composition refers to the relative mass or proportion of each element in a compound, expressed as a percentage of the compound's total mass. It indicates the composition of a compound by weight. Shown is the equation that will be used in order to compute the percentage composition. To calculate the percentage composition of a compound, you determine the mass of each element present in 1 mole of the compound and divide it by the mass of the compound. Then multiply by 100 in order to express it as a percentage. In order to understand how the equation works, we have an example. We have PCl5, which is phosphorus pentachloride. First, we have to find the molar mass of all elements in the compound. For phosphorus, we have 30.974 grams, and for pentachloride, we have 5 times 35.45 grams, which is equals to 177.26 grams. Next, we have to find the molecular mass. For the molecular mass, we just have to add the grams for the phosphorus and pentachloride. We have 30.974 grams plus 177.265 grams, which is equals to 208.239 grams. Lastly, we have to divide each molar mass by the molecular mass and multiply by 100. For phosphorus, divide 30.974 grams to 208.239 grams and multiply it by 100. We have 14.87%. For the chloride atoms, Let us divide 177.265 grams to 208.239 grams and multiply it by 100. We have 85.13%. Therefore, phosphorus pentachloride is percent purity is somehow similar to percent composition. However, for percent purity, we want to know how much of the sample is pure. To do so, we would need to react a pure substance by another reagent. The formula for percent purity is percent purity is equals to mass of the pure chemical over the mass of the sample multiplied by 100. For the application of this formula, let us have a sample problem. A 970-gram sample of rock was found to contain 718 grams of calcium carbonate. Calculate the percentage purity of this sample. We have percentage purity is equals to 718 grams over 970 grams times 100. Our answer is 74.02%. Geldal method. It was developed in 19th century by Johann Geldal, a Danish scientist. This method is used in order to determine or estimate the nitrogen present in organic compounds. The Geldal method is composed of three major processes, which is digestion, distillation, and titration. Digestion procedure aims to break all nitrogen bonds in the sample and convert all of it into ammonium ions. These will happen through the addition of an acid in a 350 to 380 degrees Celsius. In the distillation process, the ammonium ions is converted further into ammonia by the addition of alkali. The ammonia is transferred into the receiver vessels through steam distillation. When sulfuric acid standard solution is used as an absorbing solution, the excess sulfuric acid will be titrated with sodium hydroxide standard solution. Let us solve a problem to determine the nitrogen component present in a compound. 65 ml of a 0.250 molar aqueous HCl is needed for neutralization of ammonia from 5.25 gram sample of organic material. Calculate the mass percentage of nitrogen in the sample. In order to get the moles of HCl, we will use its volume and its molarity. So 65 ml of HCl is multiplied by 1 liter HCl over 1000 ml HCl multiplied by the 0.250 moles HCl over 1 liter. We have 0.0163 mole of HCl. In order to obtain the moles of nitrogen, we will use the moles of the HCl. 0.0163 mole HCl is multiplied by the 1 mole of ammonia over 1 mole of HCl multiplied by 1 mole of nitrogen over 1 mole of ammonia. We have 0.0163 mole of nitrogen. In order to obtain the mass of nitrogen, we can use the moles of nitrogen. We have 0.0163 mole of nitrogen multiplied by its molar mass, which is 14.01 grams nitrogen over 1 moles. This will give you 0.228 grams of nitrogen. What we want to calculate for this problem is the mass percentage of nitrogen in the sample. The formula we can use is the mass percentage. We have 0.228 grams nitrogen over 5.25 grams sample multiplied by 100%. We have a 4.35% nitrogen.
Let us now discuss the determination of empirical formula. In this slide, this is a summary on how we can uh, get or how can we formulate the empirical formula of the specific compound. So, the fact that we can determine the empirical formula of a compound if we know the present composition enables us to identify the compounds experimentally. This procedure as follows. So first, given the mass percent. Now this mass percent should be converted to grams and then divided by the molar mass. So once we get the moles uh, of each element in the compound, then we will divide by the smallest number of the moles. Now we will get the mole ratio of each element, and then uh, we can change it to the integer subscript, thus resulting to the creation of the empirical formula of the compound. So to further visualize this, we will use the application. So in this application, suppose that in one experiment, the combustion of the 11.5 grams of ethanol produced 22.0 gram of the carbon dioxide and 13.5 grams of the H2O or water. Thus, we should calculate the mass of the carbon and hydrogen in the original sample of the ethanol. So, in this computation, we have the mass of the carbon. So directly there's the mass now instead of the mass percent. Then we will multiply it to its molar mass, which is 44.01. 1 mole of the carbon dioxide over 44.01 gram of the carbon dioxide. And then we'll multiply it to its mole ratio. And then multiply it to the molar mass of the carbon. So we would get the result of 6 grams of carbon. For the mass of the hydrogen, we get we will use the grams given, which is 13.5 grams of the water, times the molar mass of the water, 1 mole of water over 18.02 gram of water, times the mole ratio of 2 mole of hydrogen, mole ratio of the hydrogen to the H2O, which is 2 mole hydrogen over 1 mole of H2O, times the molar mass of the uh, hydrogen to get the result of 1.51 grams of hydrogen. So after obtaining the mass of the carbon and hydrogen, we can now solve for the mass of the oxygen. Mass of the oxygen is equal to the mass of the sample minus the quantity of mass of the carbon plus mass of the hydrogen. Thus, 11.5 grams minus the quantity of 6 grams plus 1.51 grams, thus resulting to 4 grams of oxygen. So now let's compute the moles using the mass obtained from each element. So 6 gram of the carbon times to the molar mass of the carbon, which is 1 mole of carbon over 12.01 gram of carbon, resulting to a zero point 0.5 mole of carbon. So for hydrogen, 1.51 grams of hydrogen times the molar mass, resulting to 1.50 mole of hydrogen. For the oxygen, 4 grams of oxygen times the molar mass of the oxygen, equal to zero point 0.25 mole of oxygen, resulting to C subscript of zero point 0.50, and then H hydrogen subscript of 1.5, and then oxygen with a subscript of zero point 0.25. And now lastly, for the to determine the empirical formula, divide the smallest number of moles to get the whole number. So uh, we will use the zero point 0.50 divided by zero point 0.25 mole, which is the mole of oxygen, then resulting to 2 carbon. And then for hydrogen, 1.5 divided by 0.25, resulting to 6 hydrogen. And then 0.25 divided by 0.25 is equals to 1 oxygen, resulting to C2H6O. And we obtain the empirical formula of ethanol. So here are a few examples for determination of empirical formula. First, here the question is, what are the empirical formulas of the compound with the following compositions? A, 2.1% hydrogen, 65.3% oxygen, 32.6% sulfur. And letter B, 20.2% aluminum, 79.8% chlorine. Since there are only present event, we will assume that there is 100 grams of the compound. Each mass present would be multiplied to the 100 grams, resulting to a 2.1 gram of hydrogen, 65.3 gram of oxygen, 32.6 gram of sulfur. And then we will multiply the molar mass of each element designated to their weight, which is 2.1 gram of hydrogen times its molar mass, resulting to 2.08 mole of hydrogen, 65.3 grams of oxygen times its molar mass, then resulting to 4.081 mole of oxygen, then 32.6 gram of sulfur times its molar mass is equals to 1.017 mole of sulfur. Then this gives us this formula below with the subscripts of the uh, decimals, now a number with decimals. Then we determine which of this mole has the lowest number, and then we will divide it to give to in order to compute for the empirical formula. So the lowest mole is for the sulfur, which is 1.0 17 mole, and then as we divide it to each mole of the elements, then the empirical formula is H2SO4, which is a hydrogen sulfate. So now let's compute for letter B. Since it has the same situation with letter A, it doesn't have any given mass, we will assume that there's 100 grams of the compound. Then 100 gram of the compound will be multiplied to the percentage of each given element so that we can have the masses of each element. So there would be 20.2 grams of aluminum times its molar mass, then resulting to 0.7487 mole of aluminum. And then for chlorine, 78.8 grams of chlorine times its molar mass ratio, then it is equals to 2.251 moles of chlorine. Now, since aluminum has the lower uh, value of moles, we will use it to divide uh, the mole of each element, resulting to the empirical formula of aluminum dichloride. So, for our third example, alkene is the compound responsible for the characteristic smell of garlic. An analysis of the compound gives the following percent composition by mass, which is the carbon 44.4%, hydrogen 6.21%, sulfur 39.5%, and oxygen 9.86%. Then calculate its empirical formula. Likewise, we were going to assume 100 grams of a given compound, then multiply it to the percent composition of each element. So, uh, it will result to the masses of each present element. So for the carbon, 44.4 grams of carbon times the molar mass ratio, resulting to 697 mole of carbon. For the hydrogen, uh, 6.21 grams of hydrogen times molar mass ratio equals to 6.161 moles of hydrogen. For the sulfur, 39.5 grams times molar mass ratio of sulfur equals to 1.232 moles of sulfur. Then for oxygen, 9.86 grams of oxygen times molar mass ratio equals to 6,163 moles of oxygen. Thus, we arrive at the formula of each element: the carbon 3.097, the hydrogen 0.161, sulfur 1.232, oxygen 0.6163. Then we divide this mole by the smallest number of moles acquired, which is the mole of oxygen, 0.616 mole, which give us the empirical formula of the allicin C6H10S2O. And that's all. Thank you.